Okay, what's the input of f? What's the input of f? What is it telling you the input of f is? And what is that? What's theta? Angle measure swept out by the point starting at 3 o'clock position. Output is? Vertical height above the horizontal diameter. So, what function can we write that takes the measure of the angle swept counterclockwise from 3 o'clock and gives us vertical height in fraction of a radius? That's exactly what sine is. Is that what you're going to say? So we're calling that f, so the input is? So this is describing sine. You got all these numbers, right? You're given 13, 7.5, 2 feet. But this function is exactly describing what sine is. We worked hard on that, okay? Function g, we want the vertical height in feet now as a function of the angle. We want it in feet. So input is theta still. So here's fraction of a radius. Now we want it actually in feet. Lexi. Yeah, so if 7.5 is the radius, then sine is always going to give us the right fraction of the radius, right? Because it's a fraction of a radius length. So we want this fraction of 7.5, and then we'll get the height in feet. So we take 7.5 sine theta. That's how we think about this. Sine theta will give us the correct fraction of the total radius of 7.5. And so now this gives us feet. Okay, so h. I think this is where we left off. H is the vertical height of the point in feet above the horizontal diameter as a function of time elapsed. So h of what?
T.
Input's now t. And we want the output in feet. So that means, first of all, what if we want the output in feet? We're going to have 7.5, right? Because we're in a fraction of radius length. Is it going to be sine of theta? No, it's going to be because our input is t. So what's the argument of sine, though? In parentheses, what does that represent? An important question. Angle. So what you're ultimately putting into sine, what sine is taking, ultimately it has to be an angle. But the input of this function is t. So what we're going to have here is we're going to have an expression of t that's going to give us angle measure, right? We're going to have an expression of t there because this is a function of t. But what goes into sine is angle measure. So it'd be something like this. And so b, we got to figure out what b is, okay? What is b? Well, if we want one full cycle, what would bt have to be? 2 pi. Okay? What time will we need to have elapsed to get an angle of 2 pi? This is telling you the period here, 13 seconds. So when t hits 13, we need that angle to hit 2 pi. So that's two ways of saying one full period or one rotation. 13 seconds is the same as 2 pi. So this little thing right here will then tell us what that b needs to be so that when t hits 13, the angle hits 2 pi. So b is?
2 pi over 13.
Okay, there's other ways to think about that and come up with that. Okay? But that's a nice way to do it. When time hits 13 seconds, our angle needs to hit 2 pi. So this expression, b times 13, needs to be 2 pi when the input t is 13. And so then that means that b has to be 2 pi over 13. Does it make sense? Do you get it? What kind of quantity is 2 pi over 13t again? 2 pi over 13t? Angle measure, because that's what it's got to be what goes into sine. Okay, and that's called the argument. The input of the function is t. The argument is 2 pi over 13t. Okay, so now j. So we did not do this last time. Input of j. What's the input? So here, what's the input? T again. And now we want the vertical height. What's different about j from h? What's different about j from h? Chad. It's asking for what? Well, no, actually, the function j versus the function h. So looking at, yeah, so that's a second question, right? But up to here, it's defining a function j. How is that function j different than h? Eric?
Function h is only dealing with vertical height above horizontal diameter.
Where's the horizontal?
Function j is dealing with the vertical height above the surface of the water.
Okay, so now, the only difference is we want j to be height from the water, whereas before we were looking at height from the horizontal diameter. So how do we do that? So really then, we still want feet, so it's going to be 7.5. We still want vertical height, sine. Is our period or argument any different? That's all the same. So add 2 feet, right? What do you think? Some no's, some yeses. Some yeses. Is that a yes or no?
I was going to say, don't you just have to add that to 7.5?
To 7.5. Okay, so we got to figure out what. So there seems to be some disagreement as to what we're going to add. What feels very natural is 2, but we better make sure it's right. Okay? Because it's saying, oh, it's 2 feet above we got something that's 2 feet above the surface of the water. So don't we just take all those heights and add 2? So let's draw a picture here. Let's see. This. There we go. So let's draw a picture. So here's the water. Okay? And so where's the wheel relative to the water? So can you imagine if I'm about to draw the wheel, where would it go? 2 feet above. What's 2 feet above? The bottom of it. Okay? So here's the bottom of the wheel. It's up 2 feet. And so did you have an image like this in your mind? Okay, good. That's what you should have been imagining. But draw it. So yeah, imagine it in your mind, but draw it. Okay? But draw it. And we know that this is 2. Two feet right there. So when we're tracking the height of this point, let's talk about the maximum height and the minimum height. So what is the maximum, or let's do minimum first. So what's the minimum? The minimum height, or the minimum this function j will attain. What's the minimum value this function j will attain for tracking the height of the point on the wheel above the water? The minimum height above the water of the point on the wheel. It's height above the water. Height above the water. 2 is the minimum, right? It's always going to be greater than or equal to 2. Does it make sense? If we're this is our water now is our 0 line. Okay? So now, what's the maximum height? 9.5. What was our radius again? 7.5. So this right here is how much from here to here? That's 7.5. And then from here to the top, another 7.5, right? The radius is 7.5. You've got to make a picture. Don't try to just wing this in your imagination. The radius is 7.5. So we got 2 feet up to the bottom, then we got another 7.5 feet up to the center or the horizontal diameter of the circle, and we have another 7.5 up to the top. So what's the maximum height above the water of the point? 17 feet. 2 plus 7.5 plus another 7.5. So this function then has to have a minimum of 2 and a max of 17. Okay, so then we have this thing then called, we're going to define some terms today, the midline. Of our eventual function that we're graphing, the midline that we're graphing.
9.5.
Okay, 9.5, right? Because the midline is going to be, in this case, going to be the height above the water. So the midline of rotation, or horizontal diameter, is how high it is above the midline is at 9.5. Okay, so going back to our function here, we said j of t was 7.5 sine of 2 pi over 13 t. Now we're deciding, should we add 2? Are we adding 2? What's the midline of just sine by itself? Right now, what's the midline? What vertical coordinate will be the midline of just sine? If we were to graph this. 0, right? Sine, this function, just this by itself, what will its maximum and minimum be? So what will its min be? Negative 7.5 feet. And what will its max be? 7.5. And what do we need? We need to take these two values and add so that our new min and max are 2 and 17. Gonna add 2? We got to get that midline all the way up from 0 all the way up to 9.5. Not up 2. If you add 2, what will you get? You'll get a circular rotation that's centered at 2. Your new midline would be 2. So a lot of the wheel will be under the water. We know that the whole thing is above the water. So when you add, you think about adding the horizontal center line of rotation. That's what you're adding. So don't just pick a number off of the given information and add it on. You've got to get that center line, which is normally at 0, right? So the midline here is 0, giving a max of 7.5 and a min of negative 7.5. And we got to get that midline up to not 2 feet above the water, 9.5 feet above the water. So that way our min is going to be negative 7.5 plus 9.5 gives us our min our 2. You see that? And then our max, or a max of 7.5 of the sine. Add the 9.5, it gives us our max of 17. Don't blow it on the test. But many of you will blow it. I'm telling you right now. Many of you, here's your warning. Don't just, it says 2 feet above the water. Don't just add 2. You got to think about it. Doesn't make sense to add 2. Then the water is partially under, then the wheel is partially underwater. Okay. So that's the min, the max, the midline. We know what is our period of this function. Is the period the matter of the argument, the input, or the output? What is it? Is the period a matter of the input, argument, or output? Right, it's the interval of input, such that the output does what? Gets a full cycle of output values. So what is our period then? It has to do with t or theta? T, the input. Okay? So, what is our period? What interval of time gives us a full cycle of output? 2 pi over 13. Let's see. Braden, what do you think? What's the interval of input that gives a full cycle of output? Again, is it time or angle measure? Time. What value of time gives us a full measure of output? Britain. 13 seconds. Sorry, is that what you're going to say? 13 seconds. That was given, right? That was given that it takes 13 seconds. If our input then of our function is time, whatever amount of time it takes to make it around, or make one full cycle of output, that's our period. So we got 13. Okay? And so then, going back to this, we have another thing here called the amplitude. Let me write that first because it associates with this. So we got the period as 13. The amplitude is the distance from the midline up to the max. From the midline up to the max. Or the distance from the midline down to the min. What is that in this case? 7.5. Okay, and then we got the period as 13. So all these things we're putting together to sketch this graph. Okay, sketch this graph. You get 17 and higher. Okay, so here's how we sketch graphs. So you get your min value first. The min is 2. So down here at 2. The max is 17. Okay? Midline is 9.5. Or this is how high the horizontal diameter of the wheel is above the water. Okay, so again, max, find the max, find the min, find the midline, over here. Okay, amplitude is 7.5, so we see that right here. So this is 7.5. That's called the amplitude. And so how does it relate to the wheel? How does the amplitude relate to the circle of rotation? What's that? It's a radius length, right? So amplitude is referring to the wave, right? The wave curve that we're going to draw. It's the height from the center midline up to the height of the wave is our amplitude, okay? So that's going to be 7.5. And the period is 13. So we come over here, here's 13. And so we mark that off. And then what do we do to help us sketch this graph if the period is 13? 4. We're going to break up into the 4 pieces. You know, there's the 4 quadrants of one full rotation. So 13 divided by 4 is 3.25. So we're going to mark off on the midline, we'll mark off 3.25, which is about here. And then we need half of 13. 6.5? And then you can either take a quarter plus a half or 3/4 of 13, however you want to do it. What is it? 9.75? It doesn't look like these distances are the same. Where did we go wrong here?
13.
Oh, 13's here. I had it at 15. Why didn't you say something? You thought it'd be funny? Alright. Alright, there we go. That looks better. So here are 4. And then, so now what are we tracking? We're tracking vertical height above the water. So does that start vertical height above the water, starting from the 3 o'clock position? Does it start at the min, or the midline, or the max? Midline. And in the first quadrant, as it rotates through an angle of pi over 2, or 3.25 seconds, 3.2, is that right? Minutes? What is it? Seconds? Does it go to the min or the max? Yeah, so in the first quarter period, or first quarter cycle, it's going to go up to the max, or up to 17. And then in the next quarter cycle, back to the midline. And we worked out that that's going to be a concave down, right? Sine curve. All right, and then in the third quarter cycle, from the midline to the min, right here. Concave up. And then in the last quarter cycle, back to midline. And then if it keeps rotating, it'll keep repeating the cycle, right? So starting from 13 to 26 seconds, it'll repeat that same cycle again. Let's see how we did. Is that the function we came up with? 7.5. 2 pi over 13x plus 9.5. Okay, nailed it. Okay, so we got these new definitions. These are now definitions that refer to this curve that we're graphing of either time or angle on the horizontal axis, and then either some kind of vertical height or horizontal height on the vertical axis. And these things help you make sense and graph a given situation. So the min, the max, the midline. Okay, notice the midline, that value of the midline, that's how much you shift the graph up or down. When you shift a graph up or down, you think about shifting that midline from 0, right? So sine and cosine have a midline of 0. And if you're going to shift it up and down, you shift the midline, and then everything else comes with it. So that's what you add. The midline is the amount that you add there. Okay? And we've worked with period, dividing it by 4, getting the 4 pieces. Have I forgotten anything? No, looks good. Okay, anybody have a question on this example? Yes, sir.
Amplitude is always going to be a distance, right?
It's a height of the curve. So amplitude is referring to this red curve that we just did, the blue curve that we just graphed. It's the height of the curve from midline to the max, or from midline down to the min.
So it's going to be 7.5 feet.
That's right. Because the units on this axis are feet above the water. Yep, feet above the water. That's right. Other questions? Okay, so I want you to open up to page 379 in your workbook. Or 279. 279. And I want you to read the setup. On page 279, read the setup of number 4. And then you're going to do C, D, and E. Okay, so read the setup of number 4. And you're going to do C, D, and E. Okay, does this, what you're seeing here on the screen, agree with what you're reading? Okay. So the setup is that, oh. So this may be obvious, but just to make sure, you got the pedal on the left and the valve on the right, okay? And what happens when we, in this particular case, when the pedal makes one full rotation, the tire valve makes 4 rotations. So that's what you're looking at here in this setup. Okay, so they want you to write a function f. And what is the input of f? They want. Adam, what's the quantity? Tell me what quantity they're talking about in f. Input. Rotation of the pedal in radians. So you want to use theta for that? That's what I heard you say. And now, what's the output quantity that they're asking for? I'm asking, so the quantity, the explanation of the quantity, not, they want horizontal distance from the vertical diameter, measured in what? Fraction of a radius length. Okay, so what will give us that? Evelyn. So what will output the horizontal distance of the pedal in fractions of radius length? Sine theta. Agree with that? Cosine theta. Change your mind? Or stick with cosine? If we want horizontal distance from the vertical diameter, it's going to be cosine. Okay, so they're talking about the pedal, but they're just talking about angle measure swept from 3 o'clock and horizontal distance in fraction of a radius length. We know that's our cosine. Okay, so this angle, so theta then is the angle measure, it's the pedal angle measure. That's the key. Okay, so theta is the pedal angle measure. Now they want the tire angle measure in terms of, in terms of the pedal angle measure. So given any pedal angle measure, so come back here. So if I sweep the pedal, say this far, how would you calculate the tire, how far the tire, the valve, so the valve here, based on that angle theta, how would you calculate how much the valve rotated? What's that? He wants to multiply it by 4. Yeah, it's always, that was the setup. The tire valve is always going 4 times as far around as the pedal. So the valve angle measure would be what expression? 4 theta. Okay, so now what's the output of, so now that we want to track the, we want to talk about the tire valve, what's the output of the function g that they define in E? What's the output of that function? What are we talking about there? Riley, what do they say is the output of the function g?
The horizontal distance of the valve from
Horizontal distance of the valve from the vertical diameter. So in general, what are we going to use to build this function g if we want the horizontal distance of the valve? Cosine. So here's the key question. If g is outputting the horizontal distance of the valve, then what angle needs to be the argument of cosine? What angle measure needs to be the pedal angle measure or the valve angle measure if the output is going to be the horizontal distance of the valve? The valve, right? So if we want the output to be the horizontal measure of the valve in fraction of a radius length, then that argument into cosine needs to be the valve angle, right? So it makes perfect sense. We need to put the valve angle into cosine, then it'll give us the valve horizontal distance. So, but we want to write this function in terms of the pedal angle. We want the input into the function to be the pedal angle, but we need the argument of cosine to be the valve angle, which is?
4 theta.
Which we just found, 4 theta. Who's so excited? Thank you. We need to wake some people up. Thanks for your enthusiasm. Okay, so let's look at it again. Which angle is theta? Angle of the pedal. But if we want something about the position of the valve, then what needs to go into cosine? Valve angle. Valve angle. And then, so if we can do cosine, it'll give us horizontal position of the valve. But this function is a function of the input of the pedal angle measure. So we're saying how much do we, when we rotate the pedal so much, then we're tracking the horizontal position of the valve. Okay? But in order for that to happen, our argument into cosine has to be the valve angle, 4 theta. So let's talk about the graph. So if I can get this right. So we want... So can you, let's just do the pedal graph first. If I rotate the pedal, say through 4 theta, can you predict what the function, this is going to be the function f over here on the left. Can you predict what the function f will look like? You should be able to. I'm going to rotate the pedal through 4 theta. Can you sketch? So before I do that, sketch what the angle, what the function f will graph like. Do it. Everyone sketch it. Is that, did they tell you to do that?
Yeah.
Graph f. So we're going to do f first. Then part G. Part G. Go ahead and mark off 4 theta on that axis. Kind of stretch it out so that 4 theta is somewhere to the far right. You don't have to count exactly, but make that 4 theta take up the whole x-axis. How many is it about? Okay, it looks like if you count every 8 squares, every 8 squares could be pi. And you have enough room, and that makes 4 pi. So every 8 squares in your grid, make it at pi. And then 4 pi is pretty close to the right side of the x-axis. And then you're going to sketch what f is going to look like for the angle 0 to 4 pi. So in making the sketch, so at theta equals 0, will this start at the min, the midline, or the max? The min, the midline, or the max? What do you guys think back there? Alex, BJ, what do you think? It's going to start the min, the midline, or the max? The max, because we're measuring the horizontal distance, cosine, horizontal distance, which is at its maximum position when theta is 0. And then from there, it'll go to the midline when it gets to the top of the circle. And then what will it take to make one full cycle of output? What angle measure? 2 pi is the period of cosine. So it makes one full cycle of output, max to midline to min to midline to max, when that pedal rotates that first cycle, first rotation. And then it's going to repeat from 0, repeat to 4 pi. So this is what you should sketch for the angle, the function f. Okay, now we're going to sketch G. So I'm going to put the, I'm going to put the, just like your graph is going to look like the one on the right, because it's going to have both on the same. So this is still this is the function f, and so you can see it emerge here as, so that the blue is always the function f, what I've got blue on the screen. Okay? So that's still the function f. So now, what's going to happen to, what's the graph of g going to look like, function g, or cosine 4 theta? What's that going to look like? Exactly the same graph. So what is g? The input of g is the angle measure of the pedal, and the output of g is, what was the output of g again? Horizontal distance of the tire valve. So watch the tire valve. We're going to track its horizontal distance as the pedal turns. What is it doing? It's rotating 4 times as fast because its angle measure is 4 theta. So what does that mean for the resulting graph? Is it going to take longer or shorter for it to make a full cycle? How much shorter? So when will it make a full cycle? Pi? So watch the tire valve. It's made it once around right there, right? When the pedal's only gone a quarter rotation, the tire valve makes it all the way around because it's going 4 times as fast. So what about the period of G? Smaller or greater? It's going to get crunched like this, right? You're going to get a whole full rotation when the pedal only makes a quarter rotation. And for every quarter rotation of the pedal, you're going to get a full rotation of that tire valve. And so can you imagine, what will the graph look like? Draw it with your finger. Like this? No. Like this. Ready? Anything to wake you up? Here we go. Ready? Watch it. So there's our quarter rotation of the pedal. The tire valve made a full rotation. Another full rotation, another one. So how many rotations does it get? So when the pedal makes it around once, the valve has made it around 4 times. And so that horizontal position tracks up and down fast, right? So the moral of the story is, when you multiply the input by, say, 4, what happens to the period? Does it get 4 times as long? 1/4 is, 4 times as short. 4 times as short. And that crunches the period together. Why? Because that angle is turning 4 times as fast. So it's gonna oscillate 4 times for every 1 oscillation of theta. Okay, so you have written homework Wednesday. There will be web work that goes up Wednesday. Yeah. For Wednesday. Do Wednesday.